Okay, so thank you very much for the introduction. I appreciate it. Thank you very much for having me. It's fun to be back here. When I was actually in school, they had just built this part of the building just as I was graduating, and my last job as a grad student was to move my reactor from McCullough to that wing over there. So for you in Silicon CVD, which really should be done here, not in McCullough. I have to say, it's really amazing we used to do that back then. In any case, it's great to be back. This talks to me a little bit different, I think, than most of them, in that I'm not going to dive really deep into a lot of depth on the material side. I run the Almaden Research Lab down in San Jose. We're doing a lot of work in AI and quantum computing, in materials and polymers in particular. But I'm going to talk more about some of the motivations we're seeing in industry right now for sort of increasing the work back in materials and devices after many years of silicon technology kind of driving the ship when it comes to commercial uses of computing. So when we think of the future of computing, we talk about it being bits plus neurons plus qubits in the future. So the bits part is pretty straightforward. That's what we've been doing up till now for everything we do with computers and HPC, high performance computing as well. And you can think of it really as taking everything we knew about math, figure out a way then to combine it with digitization and information to really be able to do useful things with computing. And it served us quite well up till now. As was stated earlier, one of the early speakers was Andy Grove. Moore's Law, of course, what started this whole process off way back when. This was the original Moore's Law plot, or a reproduction of it. And with only 4 data points, he predicted what was going to happen exponentially over the next 50 years or so, which is really pretty amazing. But I think what also was noted is that if I drew this curve out to where we are today, it's starting to creak a bit. It's not really going as fast as it used to. Even the 10 nanometer node from Intel has been slowed down at this point. And also, if you look underneath the covers, the amount of performance and things we're getting by doubling these transistors on the chip every year, it really has slowed down as well. We're reaching real physical limitations in terms of how much you can just continue to scale. So we are looking for different things in computing now to continue to drive our ability to do computations, automations, and things. So that's where sort of the next step that we see happening right now is coming. And we call this biology plus information. That's where the neurons are coming from. So really thinking about how other types of computation systems do computation. And so the brain is an obvious one to go after next. We know the brain is actually quite bad at the computations that HPC does. None of us are very good at matrix multiplications in our head, but we're really good at pattern recognition and recognizing people and sound patterns and interesting asymmetries and things that actually are quite difficult to do if you use a standard architecture or standard hardware. And in fact, I think the real renaissance in AI has come, of course, from the ability for us to now have efficient neural net technology. We actually just heard in the last talk about GANs being used, for example. There's all sorts of convolutional neural nets that are really good with images. And they are really built on the idea of a brain structure, right? Or at least what we think we understand of the brain, which is instead of trying to actually write a bunch of rules to understand patterns and things, you just basically show a network a whole bunch of images or a whole bunch of data that's been labeled, and you let it train itself to figure out how those pixels should constitute whether or not you've identified a cat or not. And a cat is, I think, a very good source of a good example because it's really some of the early demonstrations that showed really good results on images were the ability to find cats on the internet. And it's because there are a lot of cats on the internet, which is actually useful because you need lots and lots of data that's got labels on it to actually do the training. And that's really what's made the revolution for this kind of structure work. And if you think about it, all this structure is really doing is taking a number in, doing some sort of nonlinear function on it, and then sending it to the next one over where all those inputs get summed up again, and you continue on. And you vary the weights on these connections in between it, and sometimes you actually vary the weights within the actual multiplications in the neurons, but that's it. And you just keep doing that over and over until you get some sort of massive mathematical formula that comes out with this is a cat and this is not a cat. So it's really just a lot of matrix math in the end that has to be done. So the reason this suddenly got really good, and when I say really good, I mean really good, in the last about 7 or 8 years, was because we have 2 things, or 3 things really, but the most important being 1, we had enough data now, as I mentioned, to actually be able to train networks. 2, we had enough compute power to actually run really large networks, because you have to have very deep networks to make this work. And 3, I'll put in parentheses, algorithms. The reality is there's been almost very little improvement in the algorithms. A lot of them are the same as what they were using back in the 70s and such, but they just couldn't run them at a scale. Now we are seeing much more innovation there, a lot more changes in terms of what people could do with neural nets. But if you see what happened, we were running at error rates, this is for image classification, for many, many years at 25 to 30% error rates. And that's obviously really poor for anything you want to do. Right around 2010, suddenly this number plummeted. And today, for image recognition, for speech recognition, language translation, not language translation, language recognition, the best trained neural nets are actually better than humans. Their error rates are actually better than what we can do. So that's really because we have the ability to have this. And it was not just the largeness of the computation scale that made it happen, but also the emergence of GPUs, graphic processing units, for doing it, because they turn out to be much more efficient at running these algorithms than just a standard computer does. I just want to take a small sidestep into where we see AI going, because I think that's important to think about too. We really do think it's going to be a really large part of the workloads going forward, which is why we're focused on what hardware would run it most efficiently. We feel like we've kind of moved through the narrow AI range. That is, we've finally proven we actually can do things like identify cats on the internet and things. Turns out you can't make much money doing that, so you got to do something else with it. So we have to go now to the stage of going from sort of like a parlor trick to something that's actually part of a workflow, that's part of what you would do in your daily job. And that's what we're really calling the era of broad AI, where we need to be able to take this, figure out how you do sort of multimodal calculations, how do you combine this with standard computations and things you're doing. If you think about being in a doctor's office, how's a radiologist going to use this to help them when they look at radiological films? If it just identifies blips on x-rays, we could already do that before. That's not really very useful. If it could also read the electronic medical record and know what the clinical test results are and understand the demographics and then come up with, hey, this is something you should look at, that's quite useful. So that's the kind of thing we mean when we go into broad AI. And I also point out that during that phase, this idea of AI replacing all of our jobs is probably a bit overblown at this point. When we can see right now, our AI is not nearly that good. It is very good at automating things, just like we've always automated stuff with computers. So there certainly will be a class of work where certain parts of it are no longer necessary, but in most cases that will just mean it's freeing up the person to do sort of the higher level work. So the radiology example, for example, it's really unlikely it's going to replace a radiologist anytime soon, but it certainly can make a radiologist much more productive, as well as reduce error rates. Just eye fatigue from looking through MRI scans alone is a huge cause of error right now in the medical industry. Now, at some point we're saying 2050 or beyond, we may hit the point of general AI, where then you'd actually see something that might look like what we would actually call intelligence, not what we actually see today. And that's when people get all worried about the robots and our new overlords and such. But we think despite a lot of the concerns, that really is a long way off. The way we do AI today, we are not close to where we are there. So we have a long time in this broad AI range to really figure out how we can make it useful, how we can grow it into being the same kind of revolution we saw with computing in the past. And there's really three things we're working on doing that. One is just advancing the AI itself. There's a lot of things we do not understand about neural nets and artificial intelligence and how you do this. So that's one key. The other is figuring out how much we can trust it. There's a lot of discussion right now about the ethics and biases that go into AI. Like everything else, if you put in biased data, you're going to train it really well to know those biases. So you've got to figure out how you're going to balance that out. And then what I'm going to talk about mostly today is the scaling of it, because the reality is it is quite compute intensive to do these things today. So we need to really figure out new hardware to actually go and make AI run efficiently in the future. So today when we talk about running neural nets, we mostly run them in the cloud, in large data centers, on large racks of GPUs and such, as I said. And that will continue most likely in the future, particularly for the training phase, where you really are trying to do the training of the systems. It takes huge amounts of data, lots of computations to actually set all those weights in that neural net. On the edge, though, we'd like to see it start to emerge eventually as well, particularly in the inferencing mode, when you have it fully trained and all you're trying to do is now use it for things. You think about it today, like when you talk to Siri, a lot of the language understanding actually happens because it goes up to the cloud and understands what you said and it gets sent back down. So you have that kind of annoying pause before it gives you the wrong answer. It'd be really nice that we're fast, so at least you'd know right away that she got it wrong. But that's something that requires a huge change in how we actually do the hardware there. And again, I'm talking largely about the neural nets. I just want to point that out because there's a lot of other classes of machine learning and analytics that we will continue to do, including so-called big data analytics or data science work that was really the precursor to it. That still runs largely on CPUs. As you get into the machine learning and things where the patterns of math become repeatable enough or uniform enough that it makes sense to think about the architecture, that's where you're really going to see some advantage by changing it. As I said, today it's largely done on GPUs, graphic processing units. It just turns out that the math you need to accelerate video games is the same math you need for running a neural net. and you can think what that means about our brains and video games. In any case, that's been working well, but we are also seeing more experimentation now with FPGAs, so actually trying to find new structures that could run them more efficiently, and starting to see some ASICs coming out, like Google's TPU, for example. It was set up specifically to try to run neural nets, because it does appear this is going to be a big enough workload to justify that. So if you think about GPUs, I said they're more efficient, but let's think about what we really mean by efficient right now. So if I wanted to do a full training on ImageNet, which is sort of the big image set of database that was put out here actually originally by Fei-Fei Li here at Stanford, and run a big network on it, I could use four GPUs. It would take me about 16 days to train fully on that, on all those classes, and consume 385 kilowatt hours. I could, of course, use more GPUs, 256 GPUs in that case, and get it done in 7 hours. But of course, consuming a little more power and energy along that way. So really, one model training is running about 2 weeks of home energy consumption. So not a very efficient way of identifying cats on the internet. So we do need to figure out ways to make this much more efficient if we want to make this more widespread, particularly if we want to be able to move into lots of different domains and train on lots of different data sets along the way. So the roadmap we see going forward right now, in the short term, obviously, we will continue to use GPUs and think about more efficient ways to build systems around them. And of course, GPUs themselves will continue to improve. And NVIDIA, of course, now when they design GPUs, is undoubtedly thinking not only about the video processing, but also how they can run neural nets efficiently. So I think we'll continue to see improvements there. And we also think about using going to more approximate computing. And I'll talk about why that might make sense, why you might be able to actually lose some precision and still have this be a useful function for deep learning. From there, we're looking at different types of materials that we could use perhaps for different devices. If you don't need to have the precision you get with a digital CMOS device, maybe you can look at analog devices and things like that. I'll talk a bit about it. And then ultimately, we do think there's a role for quantum computing here, not only for machine learning, but for other applications. But it turns out it actually can help in the machine learning space as well. So in terms of sort of near-term stuff that's going on, probably the most important thing right now is dealing with the movement of data back and forth. So the GPU itself can do, of course, the computations fairly efficiently, but it takes a lot of data to move on and off that GPU to do the training and to move the models back and forth. So if you just use like a PCIe, it's only 32 gigabytes per second, which is not really as much as you'd like for being able to do the movement back and forth. So when we designed our systems, we have now been using the NVIDIA Lynx, which is on the Power 9 processor natively as well. So you're moving about 150 gigabytes per second back and forth. And it turns out that's particularly important if you want to build really large systems that are going to have a neural net that scales really well. Because obviously, if you want to get a bunch of GPUs working together, you need to have good communication between them as well as into the Power 9 or the CPU, the Power 9 processor in this case. So we did demonstrate that you can actually get up to 95% efficiency on scaling if you use this kind of structure. And 256 P100 GPUs are what we use in this particular case. Gives a plus 4% increase in image recognition, so even better than we can do today with people. So that's a good sign that you can make some progress there. I think the most interesting thing about it is how rapidly it's also infiltrated the world of HPC, high performance computing. So the supercomputer that was announced at Oak Ridge National Lab, which IBM was one of the people building it last summer, which was the one that now brought the supercomputing mantle back to the US. It's been in China for many years. We now have the fastest one here in the US again. Was the Summit system, and it was actually 9,000 Power 9 processors, but it was 27,000 GPUs. So we actually 3 GPUs for every CPU. And it was because for the first time they said, look, we want to have a system that's just as massively scalable and huge for the AI side as for the high performance computing side, which is all, of course, about really high throughput floating point operations in most cases. So I think it's interesting how quickly that even at that scale, people are seeing the need for running AI algorithms as being critical. So GPUs, as I said, are what we use today. Unfortunately, GPUs, of course, are scaling by the same bits law that we talked about earlier. So they also are starting to roll over. This is just a projection of where we see sort of GPU performance going over the next few years. And what we really, of course, like to do is keep it going on that straight line, because in semiconductors, everything must be plottable as a line on a semi-log plot, or it's not real. This is about 2.5x per year is just empirically what we've seen happening. So how can we progress as the GPUs start to slow down? And as I said, we think there's a few steps here we can go after. So the first step would be just looking at using digital still, but maybe going with some approximate computing instead of going with the full sort of 32-bit or 64-bit floating point operations. And the reason we think it might be possible are two things. First of all, it does turn out there's a very specific kind of matrix math that is used by the vast majority of the kinds of neural nets we run right now. So you do know exactly the math you're trying to do here. So that gives you the feeling you could think about how you optimize that in the system itself and know exactly which kind of calculations you're going to run when you're updating weights and moving things back and forth. And of course, as I said, this happens to map fairly well, that red line onto GPUs. But what if we ran them at lower precision? So why do I think lower precision would work? So if you look at that picture over there on the right-hand side, you can see it's actually a very low resolution picture. Lots of bits missing, very, very low bit precision. I'm guessing no one had any problem recognizing what that is though, right? So if I asked you what that painting was, it would be very obvious to you. And that's the answer you care about. You don't actually care that it looks foggy or blurry. You know the answer. And that's exactly what you want in general from the kind of pattern recognition or AI stuff. You want the final answer, the classification, or the identification to be correct. If in between the numbers that you're getting aren't precise, it's not nearly as critical. So that's the reason we think that going down to low precision could in fact make a difference. And it's important because if you go down, every time you go down by a factor of 2 in precision, you actually gain 4x in terms of power and area on the chip. So it's actually a pretty big gain for you. So to make that work, we have to think about it across the whole stack. We look a lot at compression and quantization techniques. Can we just maybe reduce the data itself by compressing it in a bit or quantizing it into fewer steps to go into lower precision? That would help not only from the calculation, but also from the memory movement, the amount of data you're moving back and forth. Similarly on the programming model, can we find ways that we maybe don't have to move in every layer of the model, particularly during inferencing? It turns out that you could actually sometimes look at an image and within the first couple layers of neural net, you know you're close enough, you don't need to do the next 2 or 3, and you can just send in the ones 5 or 6 down. Finding a program that can understand when that's happening and quickly skip that part is also a way to reduce power. And of course, architectures itself, that's just better data flow through, so it becomes efficient. So using these techniques and a number of different ones, we were able to show at IEDM this last year the ability to get down. Instead of doing it 16-bit and 32-bit, we got down to 8-bit and 16-bit. So 8 bits for the weights, the activations, and the error and weight gradients that we use in training. We still use 16-bit for the update and accumulation as we try and when you actually add all of the inputs coming into the next node. Because if you think about it in addition, when you're doing summing, it's really important that you don't have like a really big number and a really small number in low precision that you add together and you lose a small number entirely. So you still need a little bit more precision at that point. And in fact, actually, we found also ways of changing the order in which you do the math into something we're calling chunks so that you could actually make sure you don't have this problem of losing some of the low fidelity information just because there's some strong signal on top of it. So you can see then if the black line here is the floating point 32-bit baseline, which would be sort of standard. And the red line is by using the floating point 8 and floating point 16 combination that we did. As I said, that's well, on the 32 to 8, that's a 16x improvement in terms of those portions. And on the other, it's about a 4x improvement, both for power and for area. So if we think we can do it with low precision, maybe we should think about going back to analog, because analog is quite low precision, but in fact, it's also very efficient for certain operations. And many people may remember that before, Grove and Moore realized it's all going to be digital. Analog was the way we did most computing. It just turned out it didn't scale very well because it is very error prone and not very robust. But it is very possible to consider using it for something like a low precision multiplication, which is exactly what we're looking at here. So if you think about the neural net connections here between this column and this column, basically what I'm doing is I'm taking this number, I'm multiplying it by some sort of weight, and I'm setting it over here, and this node is adding up all the numbers it gets in. So it's a pretty simple multiply and add step. So if I change the geometry here and say I'm going to put the first row here and the second row here and just put a cross point, and at that cross point, I put in a variable resistor, which I'm showing there's the phase change memory going in there. Well, if I have a current coming in from one of the nodes on the left-hand side and it runs through a resistance. Well, that's current I times R. You can do a V equals IR. That's basically a multiplication. In the end, I get all those currents running down to the bottom there at the end. They all get added up by Kirchhoff's law. So basically, by using Ohm's law and Kirchhoff's law, I've just done a complete multiply and accumulate. Obviously, a very crude one by our standards of what we normally think about for digital, but actually may be good enough. The other thing that's really interesting about this is now my weights for this model are stored directly in just the resistance of the cell. I don't need to move those model weights in and out of this design anymore. They can just sit there. So I avoid a little bit of that von Neumann bottleneck of moving huge amounts of data from the model back and forth into it. So I can just actually have the model weights sitting there. And that turns out to be at least as much of a performance advantage as using the resistance itself. So we actually did show with one of these on fully connected layers running in an image recognition neural net. We could in fact get the same amount of transfer learning from the fully connected learning as we could with normal TensorFlow, or close at least. So this was the training data initially, and then you try and show it some new images to do transfer learning on it. If you use just TensorFlow, you get those gray lines. If you use our actual physical resistors and cross points, you get something fairly close to that along the way. This was using it, the whole array was actual real hardware. We were using CMOS off chip, so it wasn't one chip together, but it was real hardware on the actual resistances. So we had all the normal error rates and problems you have with it. So it was interesting, at least, to see for the first time we were able to do it. And you also see that we were actually about 100x faster and 280x more energy efficient if you just took the parts together and extrapolate what you get when you put them on one chip. So even if you lose some of that along the way when you're trying to actually do the integration, you already have seen a pretty huge advantage over what you can do with just purely digital. However, the digital stuff we're taking down in the normal architecture to lower precision rates, we would like to get the precision of this analog multiplication up a bit because it is actually pretty noisy. So one of the things we're looking at are whether different types of structures you can use for actually doing the resistance there. So this is just a schematic here of a standard, say, phase change memory, where, of course, the way it works is you change the amount of crystallization or amorphousness in the middle of that material, and based on that, you change the resistance of the material. So in this case, when you run the current through, it heats up and it changes, it becomes more and more amorphous, and you can also cool it down and make it quench it to become more crystalline again. And normally you'd have it just like this. So obviously the resistance varies by how large that amorphous area is. The problem is that amorphous area is itself, particularly on the edges, it has traps and things in it. It tends to change over time. It certainly changes over temperature, just as the chip is operating. So that's where you lose a lot of your precision in that. So we came with a different cell design which we call projected memory cell, where in this case we actually put a cladding material around the phase change material, and that the resistance that cladding material is chosen such that when we're doing the write, we're putting in fairly high currents to actually do the heating. The majority of the heating and things takes place in the phase change material, so that changes then the size of that amorphous region. But then when you go do the read, it turns out that because the resistance is lower in the cladding area, it tends to go around that the amorphous area when it's actually being read out later on. So you're not nearly as sensitive to whether there's small changes in that amorphous region, particularly at the edges. You aren't nearly as sensitive to it. So you can get a much more linear behavior over voltage, but also, more importantly, over temperature. And what we showed is that we actually think we can get this now to have the equivalent of a 8-bit precision, which is pretty high. I mean, if you think about for an analog thing. So this is just showing over a linear rate. If you want to get exactly a double 64-bit precision would be that black line. 8-bit precision would be the green, simulated the green, and the red is what we actually were getting with the temperature compensation. So we actually were able to get really close, we think, to something that's looking like 8-bit at this point. We need to continue to improve these materials, though, and probably phase change memory is probably not the last answer for what we want to actually use for it. It's been very convenient because it's already being used for memory applications, so that's why we've explored it quite a bit. But if you want to get even further up that curve, we've got to find ways to maybe optimize the materials more. And there's been many different ways looked at. One of the things that we are most concerned about, or we would most like to see the improvement on, is the behavior of the way the memories change in resistance up and down. So your average phase change memory, when you're doing voltage pulses in one direction, it can be fairly linear, which is great. So you can kind of increase your resistance over time. When you try and decrease the resistance, it tends to just reset. So you tend to get back to the crystalline state. And you really don't want that. You'd like to be able to adjust your weights up and down, or your resistance is up and down in a nice linear fashion, ideally. So one candidate cell that we've been looking at is an ECRAM, an electrical chemical random access memory. This actually relies on actually moving ions back and forth, basically in the equivalent of a gate oxide for an FET in this case. In this case, you can actually very nice linear behavior back and forth. It's not exactly symmetrical, but it's pretty close. And actually, and the speed of that is actually fine. It's a fairly large device. It's not quite as small as we'd like it to be. So it's not necessarily the answer yet, but it's definitely going in the right direction in terms of finding a device that's got a better characteristic for being able to actually do these. We're also looking at the algorithmic side to see how much we could live with asymmetries and such. So if you had a device that looked like this, so like that's kind of a normal phase change memory, and you didn't do anything to try to compensate for that in the algorithm, you find that your error rates as you try and train the system stay pretty high. If you have a really nice ideal design like this, that's very symmetrical, and notice it doesn't actually matter whether it's linear or whether it's kind of curved. As long as it's symmetrical, you can live with that. You can get much lower error rates as you try and actually train the system. So if you actually know what this structure looks like a little bit at least, you can actually do some algorithmic compensation for it. And we think, for a while we didn't think it was going to be possible to get it as close as we ended up doing, but we found there are some tricks that you can use to try and get fairly close on that compensation. The problem is that that's extra overhead in the end for trying to actually get the circuits together for everything you would need for doing the training. So it's not necessarily what you'd like to do. You'd like to get as close as you can to linear and symmetric first, and then we do think there's ways you can actually compensate for anything that's left over in the end. So we see sort of a roadmap going forward for this, and we think this is going to become, so the equivalent sorts of races as you used to be higher and higher performance, higher and higher precision. Maybe we're going to go down towards lower and lower precision. Who can get there first? So we're down, as we said, right now to about 16 and 8-bit. We just are getting ready to publish some stuff on 4-bit for inferencing. You can usually inference at lower levels than you can for training. So when you're training, you're doing all the math to actually set all the weights. And there, it's fairly important to maintain some subtlety in terms of how much you want to change the weights as you go up and down. Once they're set, then you can actually usually quantize them into wherever they are into lower bits and actually maintain most of the precision. So we think you'll be able to get to even lower bit levels for inferencing. And that's just better, again, for even getting out to the edge if you want to do that. And that's the last thing I'll comment on the AI side. I did mention also we'd like to be able to do this at the edge at some point for good reasons. For example, a car, I mean, you've got a ton of data there. If it's going to be a self-driving car, I mean, it's got to make the decision when the pedestrian walks in front of it to stop in the next 200 milliseconds. It doesn't matter if the cloud figures it out 10 seconds later. And of course, if you have no internet, that's going to be a problem. So you clearly want to do local work there. Your mobile device, we already talked about, voice recognition, but you also have a lot of sensors on your phone that you could be taking advantage of if you could actually process that. But you have to be at really low energies, right? The whole phone is about 2 watts or so. So you really want to be at very low energies to make that efficient. But even something like security cameras, you're wired in here, so it's not a problem in terms of having power or even decent bandwidth. But you really can't send all the video from all of the cameras, say in a bank at the ATMs, to someplace and in real time figure out what's happening in the cloud. And of course, right now they tend to just put them onto a DVR, right? And then if you find out someone stole something, you go look at the DVR, the next day, try and figure out who stole it, try to figure out where they are. Well, obviously by then it's pretty hard to track anybody down. But if the camera itself could say, hey, the face of the person who's just put that card in the ATM doesn't match the face that's supposed to be the person who has that card, you could then send that signal right then directly to somebody and say, it's happening right now, and go look at this. So that's why it's really important to think about having edge stuff there. The other note I would make is we're actually creating data right now at twice the rate we're creating bandwidth. So it's never all going to go to the cloud. You can just do the math. It's just getting worse and worse. So really figuring out ways to process stuff at the edge is quite critical. So this is where getting down to really low precision makes a huge difference. We demonstrated a few years ago a chip where we put 1 million neurons and 256 million synapses on a single chip. These are all digital now, but they are really low precision, basically about 1 bit, 1 to 2 bits, about 1.5 bit if you actually go through what they're doing. And it can operate at 70 milliwatts. So that's really, really low energy. So compared to, remember, we're talking about huge numbers of kilowatt hours that we were seeing before for training. Now, it only does inferencing. You have to train it somewhere else, but it will do inferencing at very, very low energies, low enough that you could think about having that on your phone. 70 milliwatts is small compared to 2 watts. Hopefully, most of you recognize where this is. That's actually a camera on the top of Hoover Tower. We did a demonstration of that with this chip showing that it can do what you'd expect it expect a chip to be able to do, which is, in this case, following HD, high definition video, full screen, real time, following and tracking, in this case, bikes, cars, people, just identifying them, but being able to do it in real time and do it at very low power range. The other side is actually the same kind of thing, but with a mobile camera now, so the background's moving, which makes it a little bit more challenging than the fixed background we had here. So we do think there's a long way that we can go with reducing precision and finding different types of memory structures and analog devices to get AI to become much more efficient in the future. Which leads me to the last part of our 3 parts of future of computing, which is the qubits. And this is where we kind of go back to physics instead of biology to think about, are there different ways now of doing computation that we haven't used in the past? And of course, quantum computing is where this has been heading. And the main difference from a classical system that most people are aware of is if you have a qubit instead of a bit, it can actually be in a superposition of a 0 and a 1 at the same time, some linear superposition of that at the same time. It can also be entangled with other qubits so that when you measure one or manipulate one, it actually affects all of them at once. So you can see that in sort of a high level way, I'm not going to go into any of the quantum mechanics all the way down to actually writing the stuff, but it's basically allows massive parallelization in terms of some calculations. So it's going to be a very limited set of algorithms that actually will map onto quantum computers, but some of those will turn out to be, we think, quite important in terms of doing things you could never do with any kind of high performance computer. And the reason for that really is, as we start to grow these chips, they grow in a much different fashion. So the Moore's law we've been talking about in the past, when you double the number of transistors on the chip, your performance roughly doubles. I mean, it's not obviously exact, that's been roughly what we've noticed along the way. So it basically goes up by a factor of n as you go up. If you think about a quantum computer, because you have this ability to do 2 states at once and actually entangle them together, as you increase the number of qubits, your actual power or the number of states that you can represent and look at goes up by 2 to the n. So it goes up exponentially. And that's a very big difference, right? So if you have 5 qubits, that's 32 states there. If I have 10 qubits, so I double that, that's 1,024 states. So I went from 32 to 1,024 by just doubling the number of qubits, versus here you basically get a factor of 2 every time you do it. So that's actually the reason that you get a much larger performance out of them if you could take advantage of that actual, of mapping your algorithm onto that kind of structure. So this is just a picture of the IBM quantum computer. It's basically a large set of wires that go down into one chip down at the bottom. I'll show you something in a more detailed diagram shortly afterwards. But the idea is you do inputs from the outside world, which are, of course, normal bit inputs, but those go into your quantum system. You then use microwave frequencies actually to manipulate and put them into superpositions and do entanglement on them. And in the end, you do have to read out just bits. It does all have to, whenever you observe a quantum system, it always goes back to 0 or 1. So then you read out a string of bits with your output. And hopefully, if you've done it right, the manipulations there have, of course, found the right answer or state you were looking for when you actually read it out. It's a very beautiful system, but I will also say this is the reality, how the system is right now. So it's almost like back when ENIAC was formed. We literally are programming the thing by moving wires around to plug into the systems that send in all the analog signals. This is an all analog system in this case. It's using Josephson junctions and doing all the writes and reads with 5 gigahertz microwave signals that go in and out. So we really are at the beginning of quantum computing. And I want to emphasize that because I think things tend to get overhyped really quickly. IBM themselves sometimes overhypes things, but in this case, we're trying to be really clear that quantum computing is just getting started. We think there's a lot of potential, but we got a long way to go. The way the system actually looks a little bit more detail now, you have some sort of classical computer where you actually do the programming to actually set up, this is what I want the system to do. It then gets translated into here and basically gets a whole bunch of RF signals that go down in through the wires to the chip and then get read back out. That whole thing is in a big dilution refrigerator. It has to be very, very cold. The actual chip is at 15 millikelvin, so 15 millionths of a degree above absolute 0. Space is about 2 Kelvin, so that's much colder than outer space there. Of course, it's very electrically isolated as well. And really the goal of all of that is that the qubits themselves are in a superposition state, an entangled state. They have only a limited lifetime in that state before they decohere or actually settle into either a 1 or a 0. Right now, our decoherence times are on the order of 100 microseconds, which sounds short, but we're very proud of that. It's actually a really good number for qubits in the solid state world anyway. So we need to get that bigger over time, but that actually is all because of all the isolation work that happens. In the end, the chip itself has the superconducting qubits, and they're basically Josephson junctions is all they are. So they're non-linear resonators, so that you can actually get a spacing between your energy states. So the distance between the 0 and 1 state here is different than the distance between 1 and the next state up. And that's important. That's how you actually are able to say, I'm going to put it into a superposition state between the 0 and the 1 at the same time, and don't accidentally flip up into the other state afterwards. We also then use regular oscillators, microwave resonators, to actually do the manipulations. So by basically letting energy leak in and out of the qubits from the resonators that you have next to it, you can put it in these half states. So it's in superposition between 0 and 1 in its state. You can also use that to entangle two of them together by sending the signals together. And all of this then is happening in the analog domain, of course, at very low temperatures. The basic materials, it's on a silicon substrate still. It's aluminum oxide are what we use for our Josephson junctions. We use some niobium as well in parts of it. So the materials in some sense are fairly standard, but of course they have to operate in very non-standard conditions. And one of the biggest challenges we have right now is continuing trying to understand what are the things that are limiting our coherence time right now. So we're used to figuring out things, electrical traps and things that happen for doing normal electrical interference. And most of those we've been pretty successful at eliminating. But there's other things that are apparently limiting the state right now. We don't necessarily know what those are. So we spent a lot of time looking at the interfaces, finding different ways of growing materials to see, are there things that we're missing that could actually help us improve that coherence rate? And there's a lot of people, of course, outside of IBM as well, around the world looking at this problem. But I think it's a fascinating question because, in a sense, you don't actually know exactly what you're looking for, because we don't know exactly all the things that could make a qubit decohere or relax into a different state. We certainly notice that we have a lot more problems with them decohering when we're getting them entangled or doing sort of 2 qubit operations at once. Is that, we don't know if that's because it's always going to be that way or because of something about the way we're doing the interactions. So there's a lot of interesting questions going on at the device and materials level right now that I encourage people who are looking for new thesis areas to jump into, because we'd love to get some help on it. So once we get this all together, why do we even care about this? When I say it can do certain problems really well, so I'm just going to take an example in chemistry first. I'm going to choose a molecule I think we all love, caffeine. It's not a particularly big molecule. It has only about 95 electrons. But if you wanted to do a computation on this to get the exact ground state of this molecule, it would take you 10 to the 48 classical computer bits. So that's what it looks like if you write it out. That's a very big, very, very big high performance supercomputer. And in fact, actually, the planet Earth has only about 10 to the 50 atoms in it. So that's a really big computer if you're going to try and build that. So clearly, you're never going to build a classical system that can possibly explore that space and be able to give you the exact ground state. In fact, it only takes about 160 quantum bits or qubits to do that, because in fact you get all the quantum behavior of those same electrons using the qubits, because they themselves are quantum. So that's the power of going with this exponential sort of entanglement for the kinds of problems that can actually utilize it. Now, of course, what we do instead is we certainly do lots of chemical simulations all the time, but we use approximations and various shortcuts and things to be able to make them tractable. So what quantum offers is the possibility potentially to be able to do them much more exactly along the way. But it's not just the number of qubits, and I want to emphasize that because you're already hearing the qubit war out there. People saying mine's 50 qubits, mine's 72 qubits. You hear this going on. D-Wave's got 2,000 qubits. But it really matters a lot, not just the number of qubits, but also whether they're entangled or not, how well you can entangle them, and also what their coherence time is, because that tells you how deep your circuit can be, how many actual manipulations you can do before they're going to actually decohere. So we've introduced a concept we're calling quantum volume. And unfortunately, I don't have the reference. Please look this up if you're interested at all, because it's one we actually put out to the academic community, and we're trying to figure out if this is the right measure for how you could go apples to apples on the performance of a quantum computer. But the idea is you have to measure both those things, and you come up with what the volume is. So as an example, if you're at 50 qubits and you don't decrease your error rate any, and you go to 100 qubits, you find your quantum volume increases 0, because you can't actually get a deeper circuit. You aren't really taking advantage of all those extra qubits that are out there. On the other hand, if you stayed at 50 qubits but actually got a 10% decrease in your error rate, you'd actually get a quantum volume increase of almost 500x, because suddenly you can have a much deeper circuit you can produce. And so what you could actually do with the system becomes much more powerful. So we don't know if this is exactly the right measure, but we think it's heading the right direction. And at least so far from the academic community, the input's been fairly positive. So we'll see what happens as we go forward. But finding a way to do it apples to apples is going to be really, really challenging. But eventually what we'd like to do is come up with sort of the equivalent of Moore's Law. We have doubled the amount of quantum volume for the last 2 years within IBM. So far, so good. We're calling it Gambetta's Law. Just Jake Gambetta is one of our researchers, and we're trying to make it stick. But so far, it's just us. But that's okay. Anyway, 2 years in a row we've done it. But remember, they only had 4 points, and it went forward. So we have high hopes for quantum computing going forward in the future. But I also know too, if you got the volume up right, by the time you get to about 50 or 60 qubits, if they have enough long enough coherence time, you already can start to do some formulas and things in chemistry you couldn't do any other way. So we don't have to get to sort of the millions and millions of bits it took to really make computing become widespread. But we do have to make sure we have the error rates that allow it to continue to happen. So what kinds of problems could we solve? So obviously there's a lot of easy problems that we already can solve. There are hard problems for classical computers that we can't necessarily solve even on the largest machines. Some portion of those are quantum possible. I'll be really clear. NP hard problems are actually not quantum possible. They may get some acceleration from quantum, but they won't get enough to actually go solve the traveling salesman problem. You just can't solve the open traveling salesman problem on a quantum computer. At least we don't believe you can anyway, the way you could any better than the classical machine. But some of the quantum possible ones, chemistry and material simulation are really high on that because your ability to actually simulate quantum systems is quite high. Machine learning, as I said, is also one where we think we have some advantage, and I'll show you one example of that. And then optimization. So this is very interesting in the finance community. So in fact, a lot of members of our IBM Q group are actually banks and things looking at how you could use optimization for making more money along the way. So it's interesting to see where that goes. Factoring is the one that people, of course, always think about and worry about. That's when we break the internet because we can break all encryption. So a couple comments on that. First of all, you have to have probably millions of qubits, and they have to be extremely error-free qubits before you can really factor any number that would actually affect the kind of encryption we use on the internet today at 128-bit or even 256-bit. So that's a decade away conservatively. It could be a couple decades before we got there. So we have a long time on that. The other good bit of news is that already today you can use some types of classical cryptography which are quantum immune, or very quantum. Quantum immune is not a bad term for it, because those problems, that math does not map onto a quantum computer particularly well. So even when you have a quantum computer, you won't be able to do that math any better than you can in your classical system. So lattice cryptography is one class of that type of cryptography, and that's one we're really pushing on within IBM because it can be fairly numerically efficient even on a classical system. So it's almost as efficient as what we do today for public key work. So it's one that seems very possible. It also has a potential for doing homomorphic encryption, where you can keep all your data always encrypted, even when you're doing calculations on it, which would be great for security. So that's where we're kind of leaning. And what we tell people is, if you're talking about just today you don't have to worry about breaking the internet, but if you're talking about archiving things, Lincoln's from our tape group, for example, where you put things on tape archive. If you want putting something in a tape archive today that you still want to be private 10 and 20 years from now, it's not too early about thinking about encrypting that in something like lattice cryptography, because you aren't going to go back and re-encrypt your entire archive of tape, 20 years from now to make it immune. So in banking industries, governments, healthcare, there are places that are already thinking about, should I maybe be encrypting something that's going to be immune to this in the future? I did mention it's good for chemistry. We did actually show on a very small system, just a 7-qubit system, the ability to simulate a very simple molecule, lithium hydride, and a couple other examples here. So clearly you can do this on a classical system, but we were just trying to show it's possible. Now, interesting, you see the dots for that. We're not actually right on the sort of known solution, a little bit off, because these are very noisy systems still. There's a lot of error in them. We actually just published, though, a paper recently where, as we started to analyze the errors, we realized we could actually inject extra error into it. So we injected more and more error and saw which way things were moving, and you could then extrapolate back down to see what it would have been with 0 error. We found you actually got a really nice curve. So these are the kinds of things we're learning as we use the systems long before they get to the point where they really can do error-free sort of universal computing. The ability to actually find ways to actually make them useful earlier on is actually really critical. In fact, combining things like normal HPC technologies will be good as well. And just to bring it full circle back to AI, as I mentioned, we do think quantum computing is also going to be useful for AI. And particularly, this is an example of a classification problem. So if you look at the simple problem up there on top, the straight line with the light blue and the dark blue dots on it. If I ask you to draw a single line that separates the light blue from the dark blue, well, you can't do it if they're all in one line, right? You can't find one line that will separate them together. So you couldn't classify them into light blue, dark blue. simply. Now, if you raise dimensionality of it, in this case, I just squared them, so that was a pretty easy dimensional raise, then you find, oh, wait, now I can. I can draw a line between the dark blue and light blue, and I can find the classification difference. And that's essentially what you're doing in these sort of massive classification problems that you do in machine learning. You're trying to take up to very high dimensionality and find a hyperplane that slices through, that separates out the data, the two data sets that you're looking at, or three data sets, whatever the classes are. So for a set of problems, so this one we used blue and gold dots in this kind of much more complex pattern. You find a quantum system can actually take that up to fairly high dimensionality, taking advantage of the exponential number of states it can represent more efficiently, and actually find a function that separates out those black and gold fairly efficiently. And so this, again, was a toy problem at this point. You could certainly do this problem on a normal system. But the thing that was interesting is that we used this to show the importance of entanglement to get to the higher number of states we were talking about. So when we didn't have any entanglement on it, you can see our error rates were not particularly good. The best we could get on average, there was something just below 90%. As we started to add 1, 2, 3, 4 levels of entanglement on it, we were getting higher and higher accuracy on it. And we're doing this because there's a lot of discussion right now about where you get your power from in a quantum computer. Is it the superposition? Is it the entanglement? How do you create the number of states? And at least in this case, it was pretty clear entanglement was the only way to get up to the number of states you would need to really to make this problem operate efficiently. So I'm going to wrap up by just saying we've got these three types of computation now that we're thinking about. Obviously, they're going to. This really is going to be the world of clouds in the future. There's no way you're going to have these quantum computers, for example, on your premise. Some governments might, but I don't think many companies even are going to want to do it. So finding ways of actually building cloud systems that can run all of these as one system in the end is really one of the goals we have right now. You want to be able to use the AI systems as accelerators, the quantum systems as accelerators, but there's no question the classical systems will still be kind of running the show and along the way. We actually think there's going to be a lot of need for intelligent automation for even writing programs in these systems. There's a shortage of software developers right now already, and it's going to only get worse in the world of AI. So we need to find ways of doing automated programming, and we are working on that as well. And in the end, we hope to create sort of intelligent applications. I just wanted to show this one because it's one that I think this audience will appreciate. We're trying to find how would you use systems that had all these components together. And one we think will be quite interesting is in the area of what we call accelerated discovery. So if you think about materials or chemical discovery today, it's still quite Edisonian in most cases, right? We do a lot of simulation work, but a lot of it ends up coming down to really just testing things out, making new polymers, making new materials, new alloys, and testing them out. Because we can't do the full simulation of exactly what we want to do. But if you could take all these things together, could you take things where you're continuing to do your high-performance computing simulation, use some quantum systems to actually do some better, higher resolution simulations in certain parts of it. In fact, a group at Almaden right now, my lab, is looking at how even before we get to really big quantum systems, could you use the quantum system potentially to do certain parts of it. Computing in the ground state is probably not what you want to bother doing, but there's certain steps in a chemical reaction that might be really interesting if you could get that part simulated. It becomes really hard to do on an HPC system. If you could do that part, then you can really accelerate what you're doing on the HPC side. And then, as we heard earlier, there's a room for AI as well. So already people are using machine learning to try and find new designs and materials and structures. We also have been using it for the same thing we do in medicine. What if it can read all of the patents and all of the journal articles out there every day and identify things that are happening and patterns that are happening and surface those up to the researcher in a way that's actually useful? You could, in theory, you can do that on Google, but all you're going to do is a bunch of keyword searches coming back, and that's not very useful. But if you could say, I'm looking for this molecule structure, I'm looking for a structure similar to this molecule, and if it understood what that meant, understood what all the words are that mean that same molecule, maybe it could go find those things. And we actually have systems that are playing with that as well. So we think this world of having applications that actually utilize all three of these is coming, and we think it should be a pretty exciting place, particularly for the world of science as well. So stay tuned. I think that's it. That's all I wanted to talk about today. Hopefully, at least I inspired you a little bit where we think computing's going and how divisive materials might play into it, and happy to take a question or two.